Hello everyone. Let's get some work done. This is Physics 120, me trying to talk to you a little bit about some of the material you need to know as we finish the course. Let's see what we can do today. We're kind of in an awkward situation. My friend here, Christian, is helping me out very much. He's behind a mask. He's not very comfortable. I'm not very comfortable being here. I guess other people have it a lot worse than we do. There's people working in grocery stores that are constantly in contact with people, and people working in the medical profession and in pharmacies that are constantly in contact with people. That's more difficult than what Christian and I are having to deal with. But neither one of us is very comfortable being here. We're going to get done. They pretty much shut the whole place down. By tomorrow, I think it's just about going to be completely shut down from what we're understanding. I think they've shut the heat down on us too, I've been told. So we're going to be fine. Let's just get through this. If, worst case scenario, I cannot finish everything, I want you to look over here where I got Physics 120. That's us. Physics 120, Topic 7, Topic 8, Topic 9, Topic 10, Topic 11, Topic 12, Topic 13, Topic 14, and those are problems from those topics. A total of 19 that I'm going to try to knock out now in the next couple hours or so. I'll do my best. I mean, I can probably get through it. If by chance somehow I fall short or I'm not doing it in the detail that you might like, all of this is in your notes. All of this is in your notes. I say this to everybody. I've been saying it from day one. You will find all of this in your notes. So if I fall short, go to the notes, look at these. These will help you tie up some of the main things I want to say, some of the main topics I want to say. This is very hard to do, guys. I'd rather have, I would have rather had the last month or two of class to talk to my students in person. So this is obviously not ideal. You've got to read the chapters to the best of your ability, look at the good summary that's in there regarding what goes on here. It's a very good book. We're lucky in that regard. So there's some good summaries at the back of every chapter. And like I said, you do have many hundreds of problems over 3 different textbooks. For our textbook, you have many problems as well, and those are going to be problems fully solved for you. They're all there. This is all in your notes. So if something falls short, go here, look at that. Do the best you can. My TAs and I are going to try to keep some kind of office hours virtually. I'm not the greatest guy with technology, so I'll see what I can do, but I will do the best I can do with the whole thing. And that's it. Whatever office hours my TAs had in the past, they're likely going to keep them, and I'm going to likely keep the office hours I've had as well. Do what you can do, guys. The curve is, the curve might get altered somewhat, might go lower, but if it goes lower, the curve is lower. If you do lower, if everybody does lower than what I want to see them do, the curve goes lower, so it's not going to affect you that much. Things balance out. I think I've already told people this kind of stuff in the past. I think I wrote it to everybody, and that's it. Let's work. I really need people's cooperation with this, guys. I am limited as to how much I can do given these circumstances, as I know that you are also. But you do have a lot of stuff given to you up front if the communication breaks down a little bit, okay? Regarding topic 7, problem 6, 56, 75, let's take a look at it. All right, guys, make sure I got all of them. Okay, it's hard to get a hold of some of this stuff that I got here, but let's see what we got. Problem number 6 from topic 7. Let's take a look at how that plays out, guys. So this does get a little rushed. Again, look at the notes. You've got everything in the notes. At least I'm pointing you to where you need to be. I mean, that might help. I hope that helps. I hope that helps a lot for you guys. Kepler's laws, and a whole bunch of other stuff in there. Okay, let's see what we got. For chapter 6, a centrifuge in a medical laboratory, topic 7 rather, number 6, a centrifuge in a medical laboratory rotates at an angular velocity of 3,600 revolutions per minute. When switched off, it rotates about 50 revolutions before coming to rest. Find the constant angular acceleration in radians per second of the centrifuge. So the centrifuge is in a medical laboratory. It rotates at an angular velocity of 3,600 revolutions per minute. When it's switched off, it'll still rotate another 50 whole revolutions, you guys, before coming to rest. Find the constant angular acceleration that will bring it to the dead stop that we're talking about. Okay, so see what we have here, guys. I'm looking at some stuff here. Forgive my confusion on occasion on this stuff. Topic 7, number 6. A lot of ways to go here. Here's one of them. Theta is omega f squared minus omega I squared over 2 alpha. Multiply by alpha on each side and divide by theta. We got to here. Well, okay. What's going on? Well, you got this thing to go down to 0. Now, there's a lot of ways to go here. Let's figure this out. I mean, there's an omega I. The initial is 3,600 revolutions per minute. 60 seconds in a minute. So that's 3,600 divided by 60 is 60 revolutions per second. Every revolution has 2 pi radians. So it's 120 pi what do we got here? Basically, that's it. A minute is 60 seconds. 60 goes into 3,600 60 times, so 60 revolutions per second. Multiply by 2 pi, and you got radians per second. The final angular velocity is 0 revolutions per minute, 0 revolutions per second, 0 radians per second. Now, you can write this any way you want. So, S or SEC to write that. There are a number of ways to go here. Probably, I mean, this is good, but there's nothing wrong with this. Your probably best bet on the whole process. Well, I mean, I think this probably is our best bet. So, this went, you got it to 0 radians per second. The other one is 120 pi radians per second, so again, this is the big one. Watch out. Watch out which one you're using now. 2 theta. 2 times theta. What's theta? Well, it's 50 revolutions, isn't it? Every revolution has 2 pi radians in it. So this is where we're going to go on this process. Knock this thing around a little bit. Does that show up okay or not? Or not? It's okay? Not bad, okay. A joke I've been making with all these classes I'm working on to do like this, the custodians find me when this thing all clears up. Who knows how it's going to end? They're probably going to throw me in the garbage. So here we are. Okay? So it's coming right here. We're really taking advantage of this room. It's a nice room for us to use, at least. That's it. It's about as simple as that, you guys. Okay. For 56, let's take a look at it. 56. Keratinocytes are the most common cells in the skin's outer layer. As these approximately circular cells migrate across a wound during the healing process, they roll in a way that reduces the frictional forces impeding their motion. Given a cell body diameter of 1.0 times 10 to the negative 5 meters, that's 10 micrometers, what minimum angular speed would be required to produce the observed linear speed of 1.67 times 10 to the negative 7 meters per second, 1 micrometer per minute? How many complete revolutions would be required for the cell to roll a distance of 5 times 10 to the negative 3 meters? Because of slipping as the cells roll, averages of observed angular speeds and the number of complete revolutions are about 3 times those minimum values. So, let me just see how they're answering that one, guys, to be really honest with you, if I even have it, and I don't have it with me, of course. The keratinocytes are the most common cells in the skin's layer. What minimum angular speed would be required? Okay, you would need greater angular speed because there is slippage, but they're not talking about that. Because of slipping as the cells roll, averages of observed angular speeds and the number of complete revolutions are about, the angular speeds are a lot greater, about 3 times greater. The angular speeds and number of complete revolutions are 3 times what they're about to be, what we find here, because there is loss. There's not enough friction. There's slipping as the cells roll. We're not going to worry about that. We're just going to look at it and say, within the context of this ideal circumstance, so to speak, what is going on? They are the most common cells in the skin. Okay, so as these approximately circular cells migrate across a wound during the healing process, they roll in a way that reduces the frictional forces impeding their motion. Given a cell diameter of this much, that's 10 micrometers, we can say a bunch of things. So diameter, D for diameter, I guess you could say. Diameter equals 2R, and in this case, it's 1 times 10 to the negative 5. That's equal to 10 times 10 to the negative 6 meters. That's 10 micrometers, which implies that the radius is half the diameter. It's half of 10 micrometers. It's 5 micrometers. All right, so we got that. Given a cell body diameter of this much, what minimum angular speed would be required to produce the observed linear speed of this much? So that's for A. You want to observe, remember the linear speed, guys, is omega times r. You want to observe a linear speed of 1.67 times 10 to the negative 7 meters per second. So let's see here. 1.67 times 10 to the negative 7 meters per second, which is the same as 0.167 times 10 to the negative 6 meters per second. You see where I'm trying to go with this, guys. And that's 0.167 micrometers per second. Let's keep them all at the same place, man. I mean, might as well. I mean, there's a lot to be said here. If the units all line up, don't worry about it. When they don't line up, there's an issue. All right, so let's see what we got. V is omega r, and let's see how this is all going to play out, man. I mean, the way we're looking at it, it might be something just as simple as this. Omega is going to be V over R, is going to be, let's see what we got here. Let's make sure that right, that is correct. No, that's fine. This is fine. Good setup here. This is all fine. The setup right here is fine, guys. 0.167 micrometers per second divided by 5 micrometers per radius. It's going to go. Let's take it. The micrometers are going to go, and it is going to be it's going to be that, and it's going to be radians at the end of that. So let's see what we got here. When you look at it, let me just try to think here exactly how I want to talk about this. 30, 34, no, be 33.6, something like that. Okay. 0.336. I'm kind of, like I said, guys, I'm doing this cold right now, so let's see what we got. Let me just make sure that is correct. If you multiply this by the 5, you should get the 0.167. So let's see how that all works out. 0, 3, it's a little too much. So let me do something else on this. Don't want to pull the calculator out, but this is a little bit off. Not much. I think maybe the 4 would do it for us, actually. Let me try to think about it. We will 3. Yeah, I've got a feeling it's going to be this. Forgive me, guys. I'm not sure what even motivated me to go here with that, but if it's a problem I said I wanted to look at, I want you to look at it. So it's only fair that we do it. That's 20. That's 17. About right. There are 3 places here. Just think really quickly here, guys. 20, yeah, 15, 17, 1. That's 16. 3 places, 1.67. So, yeah, why didn't I pull that calculator out to begin with, right? Should be this. Which makes perfect sense, actually. Now, I mean, do they want this? You know, again, you've got the capabilities. You guys got the capabilities and the skill and the hard work and everything that goes into all this. You know how to convert radians per second into revolutions per second, into revolutions per minute, into degrees per second, degrees per minute, whatever. So this is the answer in terms of radians per second. And we'll leave it at that for now. So let's see what else they're saying here. How many complete revolutions would be required for the cell to roll a distance of 5.00 times 10 to the negative 3 meters? Because of slipping as the cells roll, averages of observed angular speeds and the number of complete revolutions are about 3 times these values. We're just talking about the minimum, guys. How many complete revolutions would be required for the cell to roll a distance of, they didn't ask us how long it took either. They just said how many revolutions. We can find out how long it took also. I mean, we take a linear speed and we could divide, nobody asked us this, but if they did, they said, well, how long does it take? Well, if I know that D is equal to this, you know, I can find that. They're not asking me that. They're asking me how many complete revolutions would occur. It's an interesting point in its own right. You understand how many circumferences would it take? You know, if I take the distance, the total distance, and I divide it by the circumference, the total distance divided by the circumference, every circumference is a revolution. Theta in revolutions. This is not generally the way it's going to go. this is the way it's going to go if you're talking about revolutions. So theta and revolutions, very important. This is just for revolutions now. Don't go doing this with other ways of looking at it. They're telling you the distance that they're talking about. We could play this a whole bunch of ways, actually. How many complete revolutions would be required for the cell to roll a distance of, assuming no slippage, 5 times 10 to the negative 3 meters. 5 times 10 to the negative 3 meters is equal to 5,000 times 10 to the negative 6 meters. I mean, I hate to pull that one on you, but I mean, the way they're saying it. How many complete revolutions would be required for the cell? How many complete revolutions would be required for the cell to roll a distance of this much? Without slipping now. It's a different dynamic if you include the slipping. The numbers are 3 times bigger for all this stuff to come out. You're going to have to roll 3 times more revolutions because it's slipping so much. We're not talking about slipping. At least the way they ask the question, they're not talking about slipping. You want this, you want it to go this far. And as we said, where was it here? To roll a distance of this much. So, you can play this a whole bunch of ways if you want, but let's just do this. This is 5,000. It's more convenient to stay here. C is 2 pi times the radius. The radius is 5 micrometers. You get why I did it now? 2 times 5, these cancel. 2 times 5 is 10. 10 goes into here. 10 goes into 5,000 500 times. Pi right here, revolutions. However much that's going to be, when we do something like that. So you can look at it. .159.1549.154, so 159.155. It would go triple this to about like 480 revolutions to accomplish that same distance because of all the slipping that occurs. But they didn't, like I said, they didn't go there. They didn't say that for us. They didn't talk about that. Some of the argument that proceeds regarding something like that. So that's 56. 6 and 56 we got done. Let's go to 75. For problem number 75, a 0.50 kilogram ball that is tied to the end of a 1.5 meter light cord is revolved in a horizontal plane with the cord making a 30-degree angle with the vertical. Determine the ball speed. A, determine the ball speed. B, if instead the ball is revolved so that its speed is 4 meters per second, what angle does the cord make with the vertical? If the cord can withstand a maximum tension of 9.8 newtons, what is the highest speed at which the ball can move? Okay. Pretty neat questions in that regard. So let's look at it. All right, for 75, let's see if we can just get that. That drawing's not a bad idea to have. All right, it is spinning around as they told us it's spinning around, I guess you could say. So let's talk. Obviously, this is probably very likely not going to be a very good drawing, but let's see what we got here. Let's talk about some of the stuff, some of the dynamic of what's happening here. Well, you've got a vertical right here. You've got the chord right here. You got a ball at the end of it. And it's spinning around right here. This right here is a 90-degree angle going out to here. This angle right here is theta. There's a lot of flexibility in that regard. Alternate interior angles are congruent, so this is also theta. It's also theta right there. The tension in the chord is T. Does that look okay? It comes out okay? All right. Tension in the chord is T. There is a, this is all in the notes as well, guys, obviously. I mean, there's the Ty, and there's a Tx, which is this way. Where is the Tx? It's really down here, but I do it this way. So here's the component here, here's a component here of the big one, right here, of T. There's a lot going on. Let me try to, again, that little trick we played here is there's mg straight down. Mg straight down, and there's a centripetal force pulling them inward. Centripetal force pulls it inward. Remember that made-up force, that fictitious force we talked about? The centrifugal force? It's as though there's some sort of sort of tendency going this way. It's as though it's going here. Well, it's got to be balanced. Who do you think is going to balance this guy? I got an idea. How about that guy? In some sense. One guy pulls in, the other guy pulls out. Another way to put it is the T sub x is the centripetal force, this one's just a mathematical ploy. It's not really what's going on, and yet it sort of feels like what's going on. You've seen me talk about this in lecture. Didn't have a lot of time to talk about it in lecture because because of everything, but anyway, it is what it is. We can't help what happened, guys. So, but basically the Tx is equal to Fc. And we take it from there. Let's see what else we can say here. This is the radius, the radius here. Radius is radius, no matter where you're talking about it. And you got all that. They gave us a couple, they told us a couple things, so, and we'll use them as much as we need to use them. See what's going on. They told us some things, and we just try to make some sense out of it. see what we got here. Gave us this. R, if this is theta, and the length of the chord is, they told us the length of the chord was 1.5 meters. 1.5 meters times the sine of theta will give you what R is. R is equal to 1.5 times the sine of theta. The sine of theta is the sine of 30 degrees, which is, sine of 30 degrees is a half times 1.5 is this. That's that. We know that. Let's come back a little bit. I already told you, my hook or crook, you guys. Christian, is this visible pretty good? That's visible, okay. I told you the mathematical ploy is, gee, this guy wants to fire out that way. That's mv squared over r, and the t sub x is the guy holding him in. If you want to look at it from the standpoint of centripetal force, the t sub x is indeed the centripetal force, and it has this magnitude, mv squared over r. My gut feeling is always, this is the way I always do it. You have to only get this right. You don't have to follow what I do. Hopefully you follow a lot of what I do, and hopefully I'm doing it right, but the big thing is you got to get it right. You got to know what you're doing. T sub x is this, FC is this, T sub x is mv squared over r. So mv squared over r is the tendency to want to get away, and you got to balance it, and that's that. So T sub x pulls this way, the fictitious force goes that way, or you can just say, hey, look, man, no fictitious force. T sub x is the amount of centripetal force that is being applied. T sub x has to equal that. Great, good enough for me. What's T sub y? Here, this is a modified tug. So this tug of war took place. It balances. T sub x equals m. T sub x equals mv squared over r. Ty pulls up, mg pulls down, they balance. So let's see what we got here. How do you want to, now you got to be extremely careful. Now's where you got to be extremely careful. Here's theta. Here is theta. What is the tangent of theta? The rise over the run. Opposite over adjacent. It doesn't look like it's tangent because the subscripts are goofy, but these are the ones you use. T sub x divided by T sub y will give you the tangent of theta. Maybe an easier way to look at it is just say, hey, look, man, T sub x is as big as mv squared over r, and T sub y is as big as mg. And the big thing is, if this guy's the magnitude mv squared over r, and this guy's the magnitude of mg, mv squared over r divided by mg, that's the ticket to get you through here. The m's go. The m's go. V squared over rg or gr, doesn't really matter a whole lot. It's looking like that. I think the way we had used it, forgive me here, the radius was capital R. It's not something earth-shattering. I think we pick up on it anyway. But just the radius in this case, don't call it small r, call it capital R. Tan theta equals v squared over gr. Okay, so that's good. I mean, if you want to now, where do you want to figure this thing out? Sure, they're asking us what are the speeds required to actually pull this off. There's a lot here that you can use. We're solving it. We're solving all this stuff in a very general sense. Again, small r or big R, that doesn't amount to a hill worth of beans, man. As long as you know what's what. Once you label it, if I did label it as capital R right here, it's it should stay capital R. So that's what we changed. All right. Solve for v squared. V squared equals GR tangent theta. V equals GR tan theta. A whole bunch going on here, guys. So you could do this, you could do that, whatever they're saying to you. Now they gave me enough and I know what to do. For this one right here, for A, V is going to be 9.8, 9.81. We're not going to nickel and dime that too much. R was 0.75. Tangent of 30 degrees. That's A. Well, hold on. Hold the phone here. Yeah, no, that's fine. That's actually fine. Should be fine. Exactly what then make sure I'm doing what they're asking me to do here. Determine the ball's speed. That's fine. They told me all that. If instead the ball is revolved so that its speed is 4 meters per second, what angle does the chord make with the vertical? Okay. Here they didn't give me the speed, but they gave me the angle. For A, they did not give me the speed, but they gave me the angle, and I solved for the speed, for A. For B, they are giving you the speed and they want the angle. Sounds good to me. Go right here. Either one of these is fine. One's born of the other. Go with this one. Go with this one. Better yet, go with this one. You know, tan theta, it's the same. They're all the same. They all come from the same place. Tan theta is v squared over GR. Theta equals the inverse, theta is going to be equal to the inverse tangent of v squared over GR. Yeah, you gotta be, it's a little more, there's nothing wrong with this. This is true, but there's more to it. Yeah, this is true. And G is G. G is G. G is G. V is 4. So G is 9.8. V is 4. True. What's going on right here? Once this thing speeds up, guys, it's not going to be taking the angle of 30 degrees. R is going to be the length, 1.5, times the sine of theta. The theta is going to be a different theta right now. It's not 30 degrees. They gave you the speed, but you don't know what the theta is. I mean, there's no point in asking you a question to which you already know the answer. Let's stay there. Let's stay with this thing. Tan theta is this. This guy's that. Tan theta is going to be v squared, speed at which it's moving, GR, that's 1.5 times the sine of theta rather interesting. So how's this going on here? What's happening here? Well, I'll tell you what, I'm going to have to figure something out. I got to multiply by sine theta on each side. And I'll go tan theta. (1.5 times g). Okay. How does that play out? Well, let's look at it. Sine theta times tan theta, huh? Sorry about these. Is this pretty clear? Is it? Right, a little bit better. Okay. Now what the heck's going on? I mean, it's not really what we bargained for, but again, you got to really watch out here. You put the 4 in here. Now remember this right here this was 4 squared. This was 9.8. This is 1.5. Yeah, I guess so. Maybe there's something here. I mean, maybe there's something I can somehow get away with something here. Is sine squared theta the same as 1 minus the cosine squared theta? Yeah, you got to remember, guys. I mean, we got to remember that 1 equals cosine squared theta plus sine squared theta. From the trigonometry that we know. So if I subtract sine squared theta on each side, forgive me, if I subtract cosine squared theta on each side, that's going to be equal to sine squared theta. I really detest this chalk. All right, it's a big move. I mean, it's a big move to make, and maybe that gets us out of the woods. Sine squared theta is this. So let's go. Let's do it. Sine squared theta multiply by cosine. Multiply by cosine squared theta. Forgive me. Multiply by cosine theta on each side. Interesting. Get everything over here and set it equal to 0. Add a positive cosine squared theta on each side. Add a negative 1 on each side. You get all this. Okay, that's pretty crazy. you're getting to there. So let me, gotta get out of there. Let's see what we got here. Let's get some stuff out of here. Let's leave where we started. That's the B. Pretty fascinating stuff, man. I mean, at some level. I mean, here's 0 is cosine squared theta plus 1.088 cosine theta plus a negative 1. If you say x equals cosine theta, then x squared is going to be cosine squared theta, and 1 is just 1. So leave that as is, write it like this. Yeah, I mean, go for it. Do the Pythagorean Theorem. And not the Pythagorean, do the Quadratic Formula, rather, I'm sorry. Do the Quadratic Formula. And so you end up getting, you do this, and you end up getting x is equal to the cosine of theta. X equals the cosine of theta. You're solving for x. Do the Quadratic Formula with this. You know how to do it. And you're getting cosine of theta is 0.5945 for one of them, and negative 1.682. There is no negative, there is no quantity, there is no cosine. There is no cosine that has a magnitude bigger than 1. There is no cosine that has a magnitude bigger than 1. This is an extraneous solution, doesn't count. This one does though. Get the inverse cosine on each side. Get the arc cosine of 0.5945, and that will imply the theta equals 53.52 degrees. Makes sense. Remember, they sped it up. I mean, it was going earlier when they were talking about this thing. The thing was going. It was rotating. Determine the ball speed, and we figured out the ball speed, you guys. We figured out the ball speed to be about a little more than 2 meters per second. A little more than 2 meters per second. If you speed it up to 4 meters per second, you know the circle's going to get wider. If the circle gets wider, the angle's going to be bigger. It was about 2.06 meters per second at the 30-degree angle. Yeah, at the 30-degree angle, it was going at a speed of 2.06 meters per second. If you increase the speed to 4 meters per second, the circle's going to get broader, the angle's going to get bigger. It's going to go from 30 degrees to 53.52 degrees. Again, look at how this all happened again. You didn't know what the angle was. The angle got bigger than 30 degrees. It wasn't, this drawing, so to speak, is forever valid throughout this entire problem. There's nothing wrong with this drawing, and you can apply it to practically any angle, any speed, any tension, any mass, anything. This is fine. This is basically the argument, the mathematics, to make this thing happen. It's here from the ceiling, it's hanging from the ceiling, the whole thing, it's doing it. This is fine. We use it for parts A and B and for a lot of other things that we can do. When they gave us the 30-degree angle. If they don't, The angle is just going to be theta. You got to find it out. Well, as it turns out, they said, okay, you can do all the mathematics you want to do. We remember that. Sounds good to me. Let's figure this out. They gave me v squared. They gave me g, which is a constant. They didn't tell me what r was. R is 1.5 sine theta. R is 1.5 sine theta. This is tan theta. That's the reality. When you plug all that in there, this is what you got to solve. You don't know what the sine of theta is because you don't know what theta is, which means you don't know what the tangent of theta is. But I do know that v squared over gr is tan theta. V squared over gr is tan theta. I just don't know what the r is because I don't know what the angle is. So this is the problem, right here. Multiply by sine theta on each side. When you multiply by sine theta on each side, you get to here. The tangent of theta is sine theta over cosine theta. Sine theta over cosine theta is tangent of theta. Multiplied by sine theta, you get down to here. All this comes with you. You plug in here. What is this guy? This was 4. 4, 9.8, 1.5. Okay, got down to here. Multiply. You do whatever you want to do at this point. I mean, at this point, say sine squared theta is 1 minus cosine squared theta over cosine theta. Now, we could play this probably in a bunch of ways. Easiest is probably this. Multiply by cosine theta on each side and get to here. Once you get to here, get cosine squared theta over here. Add a positive cosine squared theta on each side. Add a negative 1 on each side. Everybody's gone over here. You set it equal to 0. Everybody's gone over here. You got 0 over there. 0 equals all this. X squared is cosine squared. X is cosine. 1 is 1. X equals cosine theta. Square it, it's x squared. Cosine theta, that's just x. Negative 1, that's negative 1. The rest is the mathematics that you know how to do. Get down to here, plug into the quadratic formula, get these two answers. That's not valid. This is. There's your answer. Okay? All right, guys. That was topic 7. Let's go to topic 8.